Hello, I'm Nathan Unger from ASI Rebuilders in Abbotsford, BC, Canada. We're going to discuss how to measure the conductance of starter components. Conductance is the inverse of resistance. If we make all our measurements using the exact same current value, then all we really need is the voltage drop. This is because of Ohm's law, where resistance equals volts divided by amps. If, for example, we use a power supply that provides 10 amps of regulated current, then the resistance would be 1/10 of our voltage drop reading. If the 10 amps is constant all the time, then basically the resistance is proportional to the volts. It's just 1/10 as much. And the conductance would be the inverse of that. So the calculations are simple. However, if we compare this to a golden sample or a known good sample, then we don't even have to do the calculations. We just have to make sure that the voltage drop readings on our test subject are the same as they would be on the golden sample, using the same 10 amps of test current. So, now that we've boiled it down from conductance testing to voltage drop testing, let's take a look at what equipment we could use. You can, of course, build your own setup for around $100. I explained that in the November 2012 issue of the ERE, which ERA members can find on the website. That's what it looks like. Or you can spend more money and get a laboratory-grade conductance tester, also called micro-ohms tester, which expresses the results in Siemens of conductivity. Here's some pictures, some examples of what you could find. One item I use is this 30 amp, 30 volt power supply. It can provide regulated voltage or regulated current. To set my current, I turn the amp setting down, touch the probes together, like that, and dial up 10 amps. I usually like to set the voltage at around 4 volts open circuit when I do conductance testing, because there's less sparking that way. So long as the voltage doesn't need to go over 4 volts to maintain my current setting, this will provide me a constant 10 amps no matter what item I am testing, be it a field coil solder joint, a loose ground rivet, a poor crimped or soldered commutator connection, or the brush-to-brush lead junction inside the brush. This voltmeter is one I like because it is very sensitive. It can measure down to 10 microvolts with full auto-ranging capability. The auto-ranging is handy because I never have to worry about the settings. If I measure something and it reads 10 microvolts, because of Ohm's law, where V over I equals R, the 10 microvolts divided by the 10 amps of test current provided by the tester equals 1 micro-ohm. That's very sensitive, and believe it or not, there are many times when that level of sensitivity is useful. These are called Kelvin clips, or 4-wire connections. They allow me to have separate connections for the power supply and the voltmeter when I'm testing a sample. You can see how, even though it looks like an alligator clip, yet because the two probes are insulated, we essentially have 2 separate connections. And the same for the other plug, so that gives us our 4 connections. If the voltmeter were piggybacked on the power supply leads, like here, you'd think that would simplify it, because now you just have 2 probe tips instead of 4. However, wherever you touch the power supply leads to the test sample, there are additional voltage drops. These additional voltage drops would completely wash out your reading. And that's why you need separate probes for your voltmeter, and that's the reason for the 4-wire connections, also called Kelvin clips. So here is the correct way to connect the leads. One set from the power supply to the Kelvin clips, and the other set from the meter to the Kelvin clips. And that gives you your true 4-wire connections. Okay, now I'm going to measure the voltage drops of this commutator from bar to bar. The comm should of course be sanded clean for best results. Now there are multiple current paths in this armature, but on a good armature the lowest resistance will be always between a given bar and its adjacent one. So we'll touch the probes on. We have 0.0099, which is pretty close to 0.01. Notice we have 10 amps on the amp gauge on the power supply and 1.6 volts on the volt gauge on the power supply. Now the voltage of the power supply will change in order to maintain that constant 10 amp test current. So the first bar to bar we're measuring is 0.0099, or let's round it up to 0.01. The next one, 0.01. Next one, 0.01 again, or pretty close. 0.01. 0.01. Now here we have 0.02. It's over twice what the normal connections are. So that connection there is a bad one. It's probably open. And then after that, it goes back down. It's a little high still, 0.011. But going further, it's back down to normal. And that is how you test a commutator for good connections. Now, somebody brought up the point that how can you measure something so precisely? I mean, look at the voltmeter. It's wandering all over the place. Well, that's because the probes are open and I'm touching them. But if I put these probes on the job, immediately the voltage settles down and it becomes very repeatable, very accurate, and stable. This test setup is useful for measuring lots of other things, not just armatures. For example, the brush holder rivets for the ground brushes. Would you like to be able to compare brush grade? I've got a Hitachi brush here, and you can see by the reading it's about 734. Take another brush, same part number, made by a different manufacturer. This one reads 461. Now, that doesn't mean that this is better or worse. It just means that you can use this test device to compare so that you know if it's got the same composition as a trusted brush supplier. You can also measure the brush lead where it goes into the brush. Or how about solenoid contacts? You simply close the contacts and then you can measure the integrity, about 0.03. And again, that reading means more when you have a golden sample to compare it to. Another thing that you can measure is the connections to a cable. Many times the crimps will be cold soldered, or they'll be overheated, and the crimp will have failed to make a proper electrical connection, even though it's still mechanically sound. This one here reads about 0.25 millivolts. That's a new one. And I've seen many that were a lot worse, but that still looked good. I recommend measuring how good a connector is before you assume it's good. In this example, we have the ordinary Briggs & Stratton starter. We can check the integrity of the ground brush lead. Put one probe on the front housing of the starter, and the other two probe tips you put on the brush lead where it sticks out of the starter. You take a reading. You can compare that to the other brush, or you can compare it to a known good starter. There are other things you can do with this test setup. Things like testing diodes while still connected to the stator. You could test various stator amperages. You can test the equivalent stall current of a starter. You can test the configuration of the field coils. You can even test things like how good are the contacts on a mechanical regulator. Lots of things like that. But I'll have to save them for another time. Thanks for watching.